Okay. So lecture sheet 10, it's saying Bernoulli's equation and frictional head loss. That means it talks about how we can apply Bernoulli's equation into the real world or in the real fluid. We already started from lecture sheet 9 and we solved problem with frictional head loss, but it was given in the mentioned in the problem that frictional head loss is 3.22 meter or 5 meter. But in lecture sheet 10, we'll figure out that how you can measure the frictional head loss. And beside frictional head loss, what are the other losses in the fluid system? And what are the correction of the Bernoulli's equation? We just found that Bernoulli did not apply the frictional head loss that we applied in lecture sheet 9. Now we'll show you in lecture sheet 10 there is a one more loss and one more correction in the Bernoulli's equation. So let's go through the slide. Before that, first we need to know what is the ideal fluid and what is the real fluid. Although we already discussed it a little bit before, right? So ideal fluid, it don't have any viscosity or no viscosity, or viscous effect is negligible or zero. That is called ideal fluid. So there is no viscosity. So velocity distribution over the boundary is uniform. That means if you have a cross section of a pipe, and if you make the velocity distribution through a section, then all the velocity distribution will be same length. That means velocity at the boundary is not zero, at the middle is same. All the fluid particle travel with the same velocity. So it's saying frictional head loss, no frictional head loss in the pipe, and velocity at the boundary is not zero. That is the definition of ideal fluid or property of the ideal fluid. And real fluid, it has viscosity. So it will develop shear stress because shear stress tau, Newton law of viscosity, mu du by dy. du by dy is the velocity gradient, or we can say mu by u by y, big Y. Y is the distance between two plates, and u is the velocity of the upper plate, right? So it's saying if you have a real fluid, it has viscosity, it will develop shear stress, and there will be frictional loss in the pipe. So it's saying the fluid has viscosity. Due to viscous effect, velocity of the fluid particle at the boundary should not be zero, and there will be frictional loss in the flow. Fluid particle away from the boundary will have higher velocity, and change of velocity across the flow resulting in velocity gradient. Velocity gradient means del u by del y. Change of velocity along a direction, and there will be viscous shear resistance in the fluid. So if I draw a pipe, and if I like to observe the velocity profile of the fluid particle, then it will be like that. So what does it mean? That means fluid particle at the wall, velocity is zero. Right over here, he traveling faster than the close to the wall, but at the middle, velocity is higher. So if I think this is y, along this direction is the velocity, then along y direction, there is a change of velocity from one particle to another particle. That is called velocity gradient. Now, lot of time you go for job interview, even you call a mechanics to fix your air conditioning or refrigerator, and they sometimes they call, I need a tube. Okay, you need a pipe. So what is the difference between duct, pipe, and tube? Okay, so both term actually meaning the same. It carrying the fluid. Only difference in cross section. So normally or in general, you have circular cross section that carry the fluid, liquid, and gases, high pressure gases. Flow section non-circular are referred to is called duct. If a flow cross section has non-circular, that means rectangular, then it is called duct. Triangular duct I never seen, but might be in some situation, you know. Uh, Rectangular duct normally used when fluid is a gas, okay, or air. Smaller diameter pipe is called tube. So pipe is used normally high pressure liquid, and if is you need to move low pressure air or low pressure gas, then you can use the rectangular instead of circular. And very small diameter pipe is called tube. That is the basic difference. Now, when you will use duct, that means rectangular cross section, and when you will use the circular. It's saying for transportation of liquid, you use circular pipe, because pipe with a circular cross section can withstand large pressure difference between inside and outside without undergoing significant distortion. That means you carrying natural gas from Kumulia to Dhaka from circular cross section. Why? Because is inside it has extremely high pressure, and outside what pressure we have? We have atmospheric pressure. So inside we have pressure Pi, which is very higher than P outside. So if you have this type of situation, then you need to use the circular cross section, because if you figure out the del P, that means difference of pressure in that case is high. Okay. So when you will use circular, non-circular pipe or rectangular duct, or I might say why you are not using a rectangular pipe to carry the gas from Kumilla to Dhaka. Number one thing, there will be more frictional loss, right? In the circular pipe, major loss, that means frictional loss is low, but non-circular one is high. This is one reason. Other reason that if you have non-circular duct for high pressure fluid, inside pressure is very high, outside pressure is low, right? Then the site is work like a beam. Then in the beam, you have extremely high pressure at the bottom. And I can say the edges are the support of the beam. Then, but outside pressure is very low because the delta P is very high. So in that case, these edges of the pipe will be deflect like that. Similarly, these edges, all the edges So there will be high possibility of distortion. You can avoid the distortion if you use high thickness material, but cost will be high. So for that reason, if this delta P is high, then you need to use the circular pipe. And now in a building, you might see a rectangular duct is using for air conditioning system, because in that case, the pressure inside the duct is little bit higher than atmospheric pressure. So air can come out through the vent, air conditioning vent. So in that case, the delta P is very low. So you can use the rectangular duct. And rectangular duct velocity will be low. Velocity is low, there will be a little bit more pressure. So air will come out smoothly through the vent. That is the reason. So right over here it's saying non-circular pipe or duct usually used in an application such as heating and cooling of a building where pressure difference is very small. Okay. So those things you should remember for the exam, also for your job interview. Now, what is the laminar flow and turbulent flow? We already discussed it several times. This is laminar flow. You put dye in the flow, this is a flow is smoothly. That means this is laminar. Right here, you put dye color, you see right over here, velocity is changing. So this is turbulent, and it take little bit right over here. This is called, this region is the transition region. And after that, there is a extremely fluctuation of the velocity or transfer of momentum. That means this is turbulent flow. So flow from laminar to turbulent, it doesn't happen at the same point. It takes some time. Takes some time. That mean might be 2 seconds or 3 seconds, or might be 2 minutes. It depends on type of flow. So that within that time, the fluid travels some distance. This region is called transitional region. So until this point, your Reynolds number less than 2300. When turbulence start, Reynolds number higher than 4000. So this region is the transition region. Here is the showing that this is turbulent, and I'm sorry, laminar. This is a laminar. Then it become a little bit turbulent, again laminar. Then this region, this small region is kind of transition. Okay. In transition flow, your Reynolds number is this much. We already discussed this. So let's go through the next slide. Right over here, it's showing some real example of laminar and turbulent and transition flow. So this portion is, I'll call it laminar. After that, right, this mass portion is not turbulent yet, but like this one over here smoothly, right over here is not that much smooth, but until this portion flow is transition, and from all the region, this portion is turbulence. Okay. So you get some idea that how turbulence flow and laminar flow look like. There is a one more example. You have a candle, through the candle there is smoke rising, and you see from this portion to this portion is laminar, but from here to here is turbulent transition. Then it's turbulent start. Okay. Now you need to know one thing. that you like to attach a pipe with a tank. Say you might have a water tank or say any other chemical, liquid nitrogen, oxygen, or might be natural gas. And you connect a pipe with this tank. So when you open the gate, then fluid is coming entering the pipe. So obviously this tank is high pressure, then fluid is come out through high pressure. But at certain stage, say fluid have certain velocity at this point, okay? But it should travel more faster. Say real velocity will be this much. This much velocity, it's a 5 meter per second. So right over here, 2 meter per second, then 3 meter per second, then 4 meter per second, then 5 meter per second. That means within this region, from within this region is velocity is gradually increase, then become toward the final velocity, 5 meter per second. So this within this distance, we'll call full velocity is not developed. Full velocity is developed at this point, right over here. Because over here, we are getting velocity 5 meter per second. Then all the way, it remains the fluid passing with same velocity. Now, you like to install a pressure gauge right over here, or a flow meter, densitometer, or orifice meter right over here, where you will install. If you install a densitometer, say right this point, or you'll install this point. If you install this point, you will not get accurate result because velocity is gradually changing. Full develop velocity is not happen here. So you need to install beyond this point, right over here. You can install right over here. Better to install a little bit left side. So right over here, you are installing a densitometer or orifice meter in a full developed velocity region. Then your reading will be okay. Similarly, if you install a pressure gauge right over here, it don't work. You'll not get accurate result. You have to install right over here. So this distance is called hydrodynamic length. The distance from entry point to the full velocity development region is called hydrodynamic entry length. So you need to know that length. So other thing, in the pipe, when at the entry point, say fluid enter at the point right over here. So right over here, this fluid will not travel that much due to the viscosity. It will be stick to the wall, right? Then second one will travel this much. Third one will travel this much. Similarly, at the upper end will be like that. Okay. Then and all the middle they travel this much. Then you try to draw velocity profile at next point, say right over here. So if I make a line right over here, then still velocity of the fluid particle at the boundary is 0. Then from the boundary, this fluid will travel little bit faster. So he came in traveling more distance than him. So he traveling, say, right over here. And he traveling a little bit far, then all the fluid particle traveling the same distance. And same thing happened in the bottom. Then you try to figure out the velocity profile right over here. then you see velocity of the fluid particle again at the wall will be 0. But from the wall, he travel far distance right over here. And similarly happen in the other side. Then you take right over here, you see this particle travel more faster. This one travel more faster than this fluid particle. Finally, you take right over here, you see the maximum right over here. This one is reaches maximum velocity. And after that, velocity is not changing. Now, if you connect all the line with this maximum velocity, then you will get a line like that. Now, this line is called boundary layer because within this region, velocity of the fluid particle will remain low. For example, if you have a flat plate of your, say, your balcony, and air is coming from this side, this side in the winter or summer, whatever we say. So immediately air hit over here, its velocity will be 0. Velocity will be 0. Then you take right over here, still there will be a fluid particle close to your wall or floor. But from the little bit away from the floor, he will travel this much, he will travel this much. You take far over here, he will travel more far distance. So if this velocity is u, say 100 mile per hour, at one stage you will see right over here, his velocity is getting 99 mile per hour. So if you make the distance right over here, this thickness is called boundary layer thickness because velocity reaches 99% of free stream velocity. So this thickness is called boundary layer thickness, and this profile is called boundary layer right over here because within this region, fluid velocity will be low. So if you have pipe in the other wall, will be same thing. So you will have only better flow within the middle of the boundary layer. Okay. So let's see what they like to say. So boundary layer in a pipe flow. Consider a fluid entering a circular pipe at uniform velocity. Because of non-slip condition, fluid particle in the layer in contact with the surface of the pipe will be completely stopped. This layer also causes fluid particle adjacent layer to slow down. If this fluid particle velocity is 0, then he'll try to hold this fluid particle. He said, don't run, please stick with me. So he'll slow down his velocity, that is saying, and gradually result as a friction. A velocity developed a velocity gradient along the pipe. That means along the pipe, there will be change of velocity. So we need to figure out, we know along the length, the velocity will be changing and gradually increasing at the edge of the boundary layer thickness. So when it reaches 99% from NT point to say, I'm saying right over here, velocity of the fluid, say velocity right over here, entering with some velocity, and right over here, this fluid particle is traveling 99% of the free stream velocity. Then this length from entry point to the point where velocity developed 99% of the fully developed flow, that thickness is called not thickness, that's distance, is called hydrodynamic length, HLH. So length of pipe duct is required to achieve a maximum velocity 99% of fully developed flow when fluid entering fluid velocity profile is uniform. Right over here is uniform, but at that distance to a region where you have 99% of free stream velocity, that distance is called hydrodynamic length. So it is calling length of the pipe of duct is required to achieve a maximum velocity 99% of fully developed flow when fluid entering with a uniform velocity profile at the entry. Okay. Now, how will figure out this length, hydrodynamic length? If flow is laminar, then hydrodynamic length will be 0.05 RE, that means Reynolds number into D. That will be your entry length. If flow is turbulent, then it will be 1.359 D diameter of the pipe into 0.25 of power of Reynolds number. This is the, and this one approximately you can say this is 10D. Okay. So this is important when you like to install some equipment, the kind of sensor or a flow measuring device in a pipe. Then you need to make sure that you are not installing something within the hydrodynamic length. Length might be 2 feet, might be 4 feet, depends on the size of the pipe and what type of flow is coming. Okay. Now, one thing we need to figure out, momentum equation. What is momentum equation? You are carrying fluid in a pipeline, and sometime you need to change the direction of the pipe, right? Say pipe is coming this to the river, hilly area. Sometime it flow over the hill under the river, or sometime you need to change the direction, right? So in that case, if you change the direction of the motion of fluid, then what happens? Its momentum is changed because momentum m into mass of the fluid into velocity, right? So velocity is the vector quantity. So you see right over here, fluid entering in this direction, then it making changing in 90-degree direction. That means the velocity, it might change direction and also magnitude depending on the your diameter of the pipe. And sometime you might make a pipe kind of U-turn like this one. So if you figure out the change of momentum in this point, so this point, your velocity is along this direction, but right over here, velocity is opposite direction. So what will be change of momentum? You see, if we figure out the delta del mv, that means change of momentum, your m, even constant I am saying, okay, into. So if this V2, then you say, or you can say this V2 is opposite direction of this V1. So I am saying this is positive. So this V2 minus because this is opposite direction of, I thinking this is positive, so this has to be negative, minus V1. So finally, you are getting M into V1 plus V2, right? So you are getting M into V1 plus V2. So what are you getting? You see your momentum is increasing, and due to this change of momentum, there will be a force in the fluid, and fluid will apply some force in your pipe. And that's why if you have some uh, area where change of momentum is very high of the fluid inside the pipe, that region you have to support strongly. If you don't support strongly, then you will see there will be breaking of the support of the pipe, or your pipe might be breakdown. So you need to, when you design a pipeline, you need to make sure that due to the change of momentum, there is not that much, whatever the force, your support will able to carry that force. Okay, you need to make sure that it will not create any problem on the support and also in the pipe. So how we will figure out that amount of force? So it is called, we'll figure out by impulse momentum equation. And what is saying impulse momentum equation? It's saying impulse applied to a body equal to the resulting change of momentum of the body. So what is impulse on the body? Impulse mean if a small is a big force work for a small amount of time, that is called impulse, right? For example, you are traveling 60 miles per hour, so you have high force on energy on your half mv square kinetic energy. Then you hit a tree within second. That is the impact. You play cricket ball is coming and you hitting with higher force. What is your hitting time? Might be millisecond or 1 second. That is the impulse. So a ball coming with higher speed and you are hitting with a bat, right? So you are hitting with a bat with a higher velocity. So ball is coming along through this direction. And after hitting, he change the direction along the direction. That means there is a, due to the impact, there is a very high change of momentum because they change the direction. And if hitting that ball, how much time? If I say force F into delta T, this delta T is very small. That is called impact. Sometime you will see in the news, if there is an earthquake, they call impact of an earthquake because it's big force working for a few time. Might be 5 seconds or might be 10 seconds only. Okay. So it's saying that impulse applied to a body equal to resulting change of momentum. That means if F into delta T, that will be equal to change of momentum. That means if I use delta, that will delta mv. Okay. So normally mass did not sense, only velocity sense, right? So it's saying, and this impulse momentum equation you can also explain in terms of Newton's second law. What it's saying, second law, that resulting force acting on the body in any direction is equal to the rate of change of momentum in that direction. And if we start from the Newton's second law, then you see force into delta T equal to impulse. Again, we are saying impulse equal to change of momentum. So let's see now. So F equal to ma. This acceleration you can explain at change of velocity respect to time. right? Del B by del T. So you sense that del V2 minus V1 by del T, then you get this one, right? Now, so this equal to F because rate of change of momentum, right? As per second law, you will get the, so right over here we are. Now you see the impulse equal to F into delta T equal to change of momentum mv. So what is my F from here, from this equation? So F equal to m into del v by delta T, right? And this delta T, we can put this delta T uh, just bottom of delta V, then it giving you acceleration. But our intention to go to the fluid, right? So instead of m, instead of solid body, there is no rate of change of mass, right? Because mass remain constant. For example, you're driving a car, but instead fluid, your mass might be changing depending, fluid might be compressible due to the uh, head loss, there might be flow rate might be increase or decrease. So we are putting m by delta t. So m by delta t, that means m dot. So F equal to, we are finally getting m dot. M dot mean mass flow rate. That means coming kg per second into, you'll get V2 minus V1. Now, how we'll figure out the mass flow rate? M. M equal to Q into rho. Q is the flow rate, meter cube per second, then rho is the kg per meter cube. So multiply these two, you'll get the mass flow rate. And what is the Q? Q equal to area into V. So area into V into rho, you get the mass flow rate. So this m dot we can replace with the rho Q. So we are getting V2 minus V1. So if you apply in a fluid, then you can say F equal to, if say in a control volume, Q is different in 2 points. So right over here you have Q1, then V1, then rho 1. And right over here you have Q2, V2, rho 2. So in that case, how much will be the force on the pipe? So you'll get the subtract of these two, Q2, rho 2, V2 minus rho 1, Q1, V1. Okay. Now, if this two is same, this one is same, then there will be no force in the pipe. Okay. So force in the pipe will be equal to rho Q V2 minus V1. That means change of momentum you need to figure out due to the change of direction or change of velocity. We can solve this problem. We have 4 minutes, right?
Yes, sir.
Okay. You see, this is the pump right over here. He's taking water from your fluid from a reservoir. And the height of the pump from the, if you say this is the datum, then is 2 meter. 2 meter about 6 feet. And there is a nozzle. Through the nozzle, the fluid is coming out. And diameter of the pipe, this point is giving. So right over here, you see, even we getting the same fluid, same Q, but right over here, velocity would not be same because it's a smaller area of the nozzle, right? So over here, velocity will be high, and before the pump, velocity will be low. So what they're saying, water flowing from a reservoir by a pump, which developed a zero point 0.8 kilowatt on the flow. So that means how much power pump is giving to the fluid, or how much energy pump is adding to the fluid is 8 kilowatt. Find thrust on the pump support. You need to figure out how much thrust will be in the support. Because if you put a very weak support, then what will happen? Your pump will vibrate and then it will collapse the pipe. You putting for your home is nothing. But similar problem might be happen. Say you are carrying explosive liquid nitrogen, oxygen, or might be liquid hydrogen that is extremely uh, explosive. So that's why you need to make sure that your support is strong enough to carry the thrust of the fluid. Now, how we can figure out? So, pump power is given. Instead of head, they are giving power. So, we know that pump power equal to rho g q h. So, pump power is given, q is not given, right? Rho we know is saying water. So, rho we know, g we know, q we don't know, right? H pump, these two value we don't know. Now, we know Q equal to A into B. Any reason if you are able to figure out the Q, you can figure out the velocity at point 3 and velocity before the pump, or where we applying the boundary condition. If we apply boundary condition at point 1 and point 3, then you see how much pressure at point 1. Obviously, atmospheric pressure. How much pressure at point 3 when fluid coming out is experience, again atmospheric pressure. Then velocity at point 1 I can say 0, because if you maintaining the water tank height constant, then it has to be 0 velocity. So velocity is 0 beyond atmospheric pressure, and Z1, if this is the reference line, Z1 equal to 0, and for 3 Z3 will be 2 meter, right? So only over here V3 we don't know. If we know the V3, we can figure out the Q. We can figure out the velocity over here if you need it. Okay. So let's see how we can solve it. It will take just few minutes. If I have the math cut file right over here. Did you see the math cut file?
Yes,
Hello?
sir.
Okay.
Yes, sir.
Yes, sir. Same.
Okay. It will take just few minutes to solve it. Just 1 second. This is our problem, right? So at first we write down all the data, what is given. So you see, we'll apply Bernoulli section at point 1, at point 3. So V1 equal to 0. This is our reference line. It's a reference line right over here. So your Z1 will be then 0. Z3 will be 2 meter. V3 we don't know. And P1 will be atmospheric pressure. P3 will be atmospheric pressure. So then we apply this Bernoulli equation. What happening? Fluid coming at point 1, it has some energy. P1 by gamma V1 square by 2G plus Z1. Then on the way, he absorbing energy from the pump. Then heading toward the 3. So at 3, you are getting P1 by gamma, this energy at point 1. On the way, he receiving some candy from the pump. Then there is some loss on the way. Then with this much energy, he getting out from the point 3. Now, you see, you cannot figure out the frictional head loss over here, because frictional head loss, there is length of the pipe is not given, right? So we assume that frictional head loss equal to 0. Then you put all the data, that V1 0, Z1 0, then P atmospheric pressure you put over here, and HLF equal to 0. So you get this equation. Okay, H pump. So what is our requirement? We need to figure out the thrust on the pipe. So if we know V3, V1 and Q, we can figure out. And V1 we already know, V1 equal to 0. So we need to figure out V3 and the Q. Okay. So this is one equation. Now, you see the one clue they are giving power of the pump. So power of the pump 8 kilowatt is given. So this equation we will use. So left side will have 8,000 watt. This is the power of the pump. And Q, what is the Q? Q equal to pi by 4 D3 square into V3, right? So right over here, we put the Q, power of the pump is given, and H pump already is over here. H pump equal to this much. So this is our equation. Left side, we put the pump capacity. This is rho, this is G, this is Q, and H pump value is not given. We put as a H pump. So from this equation, we figure out the H pump. So H pump equal to this one. Again, H pump, we got this one from Bernoulli's equation. So these two equations are same. So we can say from equation 1 and 2, this equal to this one, right? So this is our equation. So in that equation, we solve it, this equation. So how we can solve it? This, is hard to solve just by simple factor. But if you have a scientific calculator, you can solve it immediately. But I was trying to show you over here that you took the math class in first semester, second semester. What is the application? Here is the application. We go through the trial and error, that application of numerical analysis. So what I did, I write down the left side of my equation, this value, right? The value remain always same constant. Then I assume the velocity. First I'm saying 20 meter per second. So my right side coming this much, left side was this much. What is the difference? Right over here, too high. Is both are difference is 0, then my solution is accurate, right? So is very high, then I think V3 equal to 10 meter per second. So this is my left side, this is my right side, this is my left side. So if see is too low, then I need to increase the velocity. So I think velocity is 15 meter per second. So this is my right side, this is my left side. What happened? Is difference is come down, little bit higher. So I instead of 14, I put little bit less, 15 from 15 to 14. So when I put 14, this is my right side, this is my left side. So it coming less, 3.28. So what does it mean? So I need to increase this value little bit more than 14. So I put 14.5. So this is my right side, this is my left side. Difference is 4.24. So I just keep it over here. But again, you can increase. You can say 14.6, then what is the values coming? So numerically, this is the application of numerical analysis. Okay, even you solve with scientific calculator, inside the calculator, the program do the same thing. Okay, so finally I got V3 14.5. So how to figure out the Q? Q equal to area A3 into B3. Nozzle diameter is given, so you'll get the Q. I get the Q. Rho is given. Now, what is the F? F equal to rho Q V3. V1 is 0. So you see V1 0. So you putting in the equation, I get this much Newton force on the pipe support. Okay. Any question? Any
Sir,
question?
one question, sir.
Yeah, sure.
Sir, the pump is pulling water, so water
Yeah.
is coming to the pump. So why we are taking the velocity 0?
Velocity 0, where we applying the Bernoulli's equation. You look right over here. Inside the pipe, the velocity is not the 0. But what we did, we apply the, anyway, your question is good question. I appreciate you that you asked that question. We apply the Bernoulli's equation not inside the pipe. Number 0.1 is outside of the pipe in the reservoir and right over here. What is the reason? We are thinking why fluid is there is no pump. Fluid will come at 0.3. Yes or no? Obviously no, if there is pump. But due to the pump, fluid is coming at 0.3 with some higher speed. What is the reason? Because he is pulling, right? You are throwing your friend with the hand. That means you energy, giving energy to him to throw or fly in the air. Same thing. Right over here, I need to say that how much energy have in the fluid. Because it's saying depth is giving how much? 1.5. That means even you pulling the water, but the depth is height is remain constant because water is coming from other source, like you might have constantly and maintaining this height. So this height is not going down. So that's why we are assuming V1 0 and pressure P1 also atmospheric pressure. Same thing over here, that pressure is atmospheric pressure because no outside only you have atmospheric pressure. That's the reason. You got it? Hello?
Yes, sir. And sir, which way thrust working, sir?
Which way thrust working? Okay. So fluid is thrust is the vector, right? So V3, which way V3 is working? Along this direction, right? So ultimately, if I draw this is your pipeline. So your thrust of the fluid is going along this direction, right? So inside the surface of the, say your pipe is making the polythene, then what will happen? Then your this thrust right over here working in opposite direction, pipe wall. Pipe wall has to resist this force coming from the pipe fluid, and your wall has to resist that force. If wall is strong enough, then he will resist, right? But there is no support. Then what will happen? This wall or this pipe, he will flow along this direction. So in the support, you have to put a reaction, and that reaction will be opposite direction of this wall. But what will be in the bottom then? In the bottom will be along this direction, right? So you see, you have this support, say supporting your pump with two angle, right? So inside the pipe is force working along this direction. You think other way. So how we can balance it? Right here, force, fluid force working to the right direction. So how much force will be in the support? Should be opposite direction, right? So this will be reaction force F. That is enough. You see how force working?
Yes, sir. Got it. Got it.
You got it?
Yes, sir. Got it.
You got it, but still, this is stable.
No, sir.
Why?
I don't. don't know. I need to review the lecture for
No,
the
no,
answer.
you don't need to review. Look carefully. This is interesting. Your ape working along this direction. So support working in the bottom. How much the height between this distance? This much. So there will be a rotation, right? Is moment working along this direction. So that means he'll try to your support rotate clockwise. That means this support will experience force upward direction, this support bottom direction. So you have to put a reaction force over here and over here. So you see the support will experience two force, this force and also some vertical force. Okay. Anyway, you got your answer, right?
Yes, sir.
Okay.
Sir, these are very complex things, sir.
Why complex things? What would you say?
This is like
Hmm.
very complex, sir. Word is not coming in my mouth. How to say it?
Okay,
Very complex.
but you understand that how force is coming from the fluid to the pipe support
Yes,
due
sir.
to change of momentum. You understand that one?
Yes, sir. Yes, sir.
Okay, you understand that one, that's enough. And way I showing you that how force working in the support, right? That is actually knowledge of your solid mechanics. And hopefully you might be learn a little bit more in the support in this from the solid mechanics. Just take just passion. Say you have pump or something. Say if this is one, right over here is the support. Say this is a tool in Bangla or chair, but is fixed in a park. You are kicking with your leg with force F, but is not breaking down. Why? Because two things might break down in the right over here, right over here, or support might be breakdown. So they are strong enough to carry this force, your kick, but support, you need to make sure support also strong. So how support is react? So support will have a opposite direction. You are pushing to a right. So support will say, hey, okay, don't push me right. I have enough force to carry you. Okay. So he will apply this much force. Now, how do you see? Is there any rotation?
No, sir.
No rotation? Again, you
Uh,
making.
Yes, sir. Rotation. Yes,
Okay.
rotation.
Upper one pulling right, bottom one pulling left. That somebody pulling your head toward right direction and your leg in left direction. What will happen? Your body will rotate. So how you going to protect this one? Rotation which way? Anti-clockwise, right? So due to that this anti-clockwise, you see what will happen? If your support is say on the clay, then what will happen? This will go down and this support will go up, right? So you need to protect that one. That means due to the rotation, this support will try to go downward, this support will try to go upward, but you have to protect that motion. How you can protect? That means if your support has to be strong enough to react that force, opposite of this force. This will be downward and this will be upward. So these two force, which way making rotation? This is downward, this is upward. That means anti-clockwise, right? And this one making clockwise, anti-clockwise and clockwise, then you become neutral. So when as an engineer, when you making the support, then you need to consider these two force, this force and this force, to make sure your support is strong enough. Okay. Hopefully you might understand.
Yes, sir.
Okay, so we can leave it here. We already took 6 minutes from you. Okay, thank you very much. And